Hello everyone. So today we shall see the multi-rate signal processing. So in the multi-rate signal processing, the idea here is in the previous couple of lectures we had seen that how to change the sampling rate, which requires some combination of interpolation and decimation. Say for example, if we want to change a new sampling period, let's say sampling period of 1.01 times t. Okay, so if you recall that we need both the interpolation and the decimation, so we want to interpolate by the factor L, which is given by 100, and decimate by M, which should be 101, because if you recall we had this mt by L, right? And the cutoff frequency of the filter, the intermediate filter, is, can say, is omega c should be pi by 101. Okay, because pi by 101 or pi by m would be lesser than pi by l in that case, right? So we require the cutoff frequency in pi by n. Okay, pi by 101. So this is how we can achieve this 1.01 times t sampling period. But this is a very crude way of doing the of computing the new sampling of the computing the new signal with the sampling period, the change sampling period. So the issue here is, so there are a couple of issues in using this straightforward approach. So the first is that you require the large intermediate changes, meaning to say that the filter, the cutoff filter which is required in the cascaded block, it could be a very lower value. The cutoff frequency could be very low, uh, which we call the, meaning to say that the denominator of it would be of very high value, right? So which requires this large intermediate changes. Now the second issue is that the large amount of computations for each output sample is required. So seeing these two issues, we aim to reduce the amount of computations first of all, and this we can achieve by this concept what we are going to discuss about the multi-rate signal processing. So the multi-rate techniques we will build upon by using based on the earlier techniques we had seen, that is the upsampling, downsampling, compressor and expander. So we'll use these techniques in a variety of ways to increase the efficiency of signal processing systems in terms of the reduction in the amount of computations. Okay, so two basic results we shall discuss under this topic. So first is based upon the interchange of filtering and downsampling or upsampling operations. Okay, the second is polyphase decomposition. So these two techniques we shall study under this multi-rate signal processing to reduce or to increase the efficiency of the signal processing system for changing the sampling period. So we shall see, first of all, we shall see that if we interchange the position of the filter with the compressor or expander, what change would be imposed by changing this position. So let's say the interchanging of filtering with compressor or expander, right? So let's first of all recall that how we use this compressor. We have this some signal x of n, and we pass it to this downsampler, which we call m, and we get some signal, right? For the moment, let's call this signal xa of n, because if you recall, we have denoted this a downsampled signal by xt of n, right? And then we use some filter h of z. Now here, if you recall in the previous topic of this compressor, we have specifically designed this filter as a low pass filter with some specific gain and the cutoff frequency. But here for the moment we are discussing in general way that given some h object, which is some filter, then if this signal xa of n is processed through this some generic filter, it would be a low pass filter as well. Then say for example we get the output y of n. Okay. Now if I interchange the position of these two blocks, this is the idea behind interchanging of filtering with the compressor, then we have this x of n change. I will call this some filter, let's say h1 of z, okay, because we don't know yet whether the filter is changed or not, and I want to interchange its position as this to give this y of n. So for example, if let's label this signal, the output of this h1 of z, it would be, let's say, xb of n, and we want to explore what is the relationship between h1 of z and h of z, right? Let assume h1 of z as h of z of n, and now we want to see that if I substitute h1 of z as equal to h of z to the power n, then we say that these two representations or these two block diagram representations are equivalent, right? And it is possible under this assumption, and we shall see that if I substitute this, whether these two block diagrams are equivalent or not, right? So let's see from the second block diagram representation in the frequency domain, it would be xb e to the power j omega is equal to, if I substitute h1 of z as this h of z to the power n, it would be h of e to the power j omega m times x of e to the power j omega. Okay, so this is pretty much straightforward. Now recall from the downsampler that if we had this block diagram which we denoted by xt of n, so in the frequency domain we have represented this, that the output of this downsampler would be xd of e to the power j omega, which would be equal to amplitude scale and summation of I0 to m minus 1 of x e to the power j omega minus 2 pi I by n, right? This would be the relationship between xt and x, and this we had seen already in the previous class. So from here, now apply this formula onto the second block diagram. So I can write my y e to the power j omega as 1 by m summation of I is equal to 0 to m minus 1 of xp e to the power j omega minus 2 pi I by m, this one, because the input signal to this downsampler is xp. Okay, now we shall substitute this xp here, and we can write this as y of e to the power j omega 1 by m I equal to 0 to m minus 1 x e to the power j omega by n minus 2 pi I by n times h of e to the power j omega minus 2 pi I, right? Because we have this vector m in the numerator which get cancelled out here, and since from this function h of e to the power j omega minus 2 pi I, where I of course is an integer, then it is equivalent to h of e to the power j omega. So we have y of e to the power j omega is equivalent to 1 by m summation of I is equal to 0 to m minus 1. Okay, so let's, because now in this part we don't have I, so I can take this part outside from the summation. So let me rewrite it once again. So it would be equal to, by taking this factor out of this summation, e to the power j omega times 1 by m I equals 0 to m minus 1 x e to the power j omega minus 2 pi I by n. Okay, now see that this is equivalent to this, and the output is xt, but this block diagram is in fact equivalent to this one. So whatever your xg is, our xa is. So I can write in my expression from the above, from the first block diagram representation, that y of e to the power j omega would be equal to h of e to the power j omega times xa of e to the power j omega, right? So this is the exact representation. Now the first block diagram, because here we have this y of n, and in the frequency domain it would be y of e to the power j omega is equal to h of e to the power j omega times xa of e to the power j omega, and this is what we get. So both these block diagrams are equivalent if I substitute h1 of z as equal to h of z to the power m, right? So if we have the downsampling operation followed by a filter, then I can interchange their position. By interchanging their position, the frequency response of the filter would change with this, and this is the change which will happen here. Now if we see for the upsampling, so similarly consider the two block diagrams by shifting the position or interchanging the position of the filter with the upsampler, right? So x of n is passed through some filter, let's call it h of z, and then pass it through the upsampler by an digit factor L, and we get this y of n. Now if I interchange the position of these two plots, I will get upsampler first and then another filter, let's call it once again h1 of z and y of n. So similarly we can denote the intermediate signal as xa of n and xb of n, right? So let's say again we say that h1 of z would be equal to h of z to the power L. Then in that case both these block diagram are equivalent. If I change the filter, whenever I interchange the position of the filter and the upsampler or downsampler, the frequency response of the filter would change, right? So this is the idea. So similarly we can write y of e to the power j omega. From the first block diagram we have y of e to the power j omega is given by xa of e to the power j omega L. This is how the frequency response of the signal changes whenever we do the upsampling operation, and we had seen this earlier. And xa e to the power j omega from the first part Basically the multiplication of the frequency domain representation of these two functions. So it is given by x of e to the power j omega l, sorry, let me write it clearly, j omega l times h of e to the power j omega l. Okay, now let's see the first block of the second block diagram. What is the output of this thing? It is xb e to the power j omega is equal to x e to the power j omega l. So I can substitute this expression in the above equation and we get y of e to the power j omega is equal to xb e to the power j omega and h of e to the power j omega l, right? And this is what changes here, right? So starting from the first block diagram, whenever I interchange the position of the filter and the upsampler, then the frequency response of the in the overall block diagram would change by this h of z to the power l. Okay, so the above these two interchanging of filtering with the compressor or the upsampler, it shows that the operations of linear filtering and downsampling or upsampling can be interchanged if we modify the linear filter. Okay, so this is the basic principle. Now let's see what how we can achieve the multi-stage decimation and interpolation, right? So whenever the decimation or interpolation ratios are large, it is necessary to use filters with very long impulse responses to achieve the adequate approximation to the required low pass filter. Because if you recall, we had the interpolator and decimation in the beginning and the end in the overall cascade block diagram, and in the middle we have the frequency response filtering or the low pass filtering with a cutoff frequency of minimum of pi by L or pi by N. But if those ratios are quite large, then you need the filters of very long impulse responses to approximate the filtering process, right? And we had seen that if we use the single operation, then it takes large number of computations. So we want to significantly reduce these computation through the multi-stage operation. And this multi-stage operation we shall achieve. Say for example, let's discuss first of all the two-stage decimation system. Okay. So in the two-stage decimation system, let's say we want to downsample the sampling period by an integer factor m, and we can write m as a multiplication of two factors m1 and m2. Of course, they should be integers. So this is what we call the two stage. So in the first stage, we shall downsample the sequence by m1. In the second stage, we shall downsample the sequence by m2, and then at the end we will see that this two-stage process is in fact equivalent to develop a decimation system where we want to downsample the sampling period of the signal by m times. Okay, so first of all let's draw the plot, and this is what we want to achieve. Given x of n, I pass it through some filter. This could be a low pass filter, okay, of the appropriate cutoff frequency or pi by n, let's say. And then we have this downsampler m and xd of n. Right, this is what we had seen earlier. if we want to develop this decimation system, but now we want to achieve this in a by two stages. Okay, so in the first stage, like I said, first we develop a decimation system so that it is downsampled by m1 and then downsampled by m2, and this can be represented by a cascaded block diagram. So in the first stage we have this h1 of z with cutoff frequency pi by m1, and then I pass it to the downsampler m1. Right? Whatever I get here, it is then feed to another filter h2 of z with the cutoff frequency of pi by m2, and this is then passed to the downsampler m2 to finally achieve this xt tilde of n. Okay, now we want to see that using this cascaded operation, is it equivalent to this one? We want to see this equivalence, right? So let's see, and we will use the same principle what we had discussed just now about the interchanging of the filtering and the upsampling and downsampling. So first of all, I will interchange these two blocks m1 by h2 of z. So I can write x of n as h1 of z, and if I interchange this block, the frequency response would change to h2 of z to the power m1. Okay, and then it is passed to the downsampler m1 and to the downsampler m2 to finally get this xt tilde of n. Because we had seen that interchanging the position of the filtering and the downsampler, the frequency response of the filter would change, but the input-output signals won't change. Okay? And we know that I can club these two frequency responses with filters, and similarly these two things. So I can write this x of n as h1 of z and h2 of z to the power m1, pass it through the downsampler m1 and m2 to get this xt tilde of n. Right? And the cutoff frequency of this filter would be pi upon m1 and m2. Right? So we can use this two-stage decimation process to achieve the downsampling by the integer factor of m. So we know that this cutoff frequency pi of m1 and m2 would always be lesser than pi by m1 and pi by m2. So we get fairly large cutoff frequency range to approximate this high frequency component. Generally these things are required in the narrow band filters, and those filters generally requires high order system functions to achieve this sharp cutoff approximation to the frequency selective filtering characteristics. So in that sense, two-stage implementation process is more efficient than the single-stage implementation process. So now if we see the frequency response of this overall filter, it would be given by h of z as h1 of z times h2 of z to the power m1, and we call it the interpolated FIR filter. Okay. Now if m has many factors, the above can be generalized to any number of stages. Likewise we did for when we wrote m as equal to m1 and m2. Okay, and this h z in the time domain can be represented as h of n is equal to h1 of n convolved with summation k minus infinity to infinity h2 of k with delta n minus k mi. Right? Now talking about the two stage, we can quickly see what would happen in the interpolation. interpolator, two-stage interpolator. So we have this x of n, and we want to upsample by L1, pass this h1 of z, again upsample by L2, and then pass it by h2 of z to finally get xi of n. The cutoff frequencies of the respective filters would depend on the L1 and L2, of course. So interchanging the position of these two blocks, we will have xn upsample by L1, upsample by L2. Filter h1 of z would change to h1 of z to the power L1. Sorry, it should be L2. L2, and finally h2 of z to get xi of n, interpolated signal. And the compact representation, we have this upsampler by L1 and L2, pass it through the cascade combination of these two filters, h1 of z to the power L2 times h2 of z, okay, xi of n. Okay, the similar process, the similar multi-stage process, likewise we see for the decimation. Okay, so in the next class we can discuss about the polyphase, the decomposition operations. Okay, thank you.